Kia ora Year 13 and Year 12. This is the first video that I'm doing on the Walker task on pages 80 to 82. It's all about mini pizzas and stuffed potatoes. So in this video I'm going to do question A, which is the first bit and very achievedy, and then I'm going to do question B, where we're going to hit multiple solutions for the first time. So I'm going to go quite slowly through this. I'm going to do some of it using the graph, but some of it we're going to need a little bit of Year 9 algebra, and in particular we need to be able to rearrange equations into the form y equals, where's my stylus gone? Here we are, y equals mx plus c, because this is the key to understanding harder linear programming problems. But first let's just get into the first bit, and I'm going to go through this reasonably quickly. We need to find our two variables, and we can see that they're going to be mini pizzas, the number of mini pizzas and the number of stuffed potatoes. What we're trying to do here is to maximize profit. So we need to calculate the numbers of stuffed potatoes and the number of mini pizzas that the canteen should make. And our constraints are given to us in here. And we've got the following constraints. We've got a constraint on how much stuff they can fit in the oven, how many ingredients they've got for the two foods, and then we've got a constraint about time. We also have to remember that we can't have negative numbers of potatoes or mini pizzas. And the profit function is given to us, well, we can make it from this information here. So let's quickly start by doing the variables. Let the number of mini pizzas be x and let the number of stuffed potatoes be y. I've had quite a few questions from people about this, and it doesn't matter which one you pick, right? But I always pick whatever's first is the x, and whatever goes second in the words is the y. The profit function I've written as 0.5x plus 0.75y. Right? So what I'm going to do straight away here is rewrite this in the form y equals mx plus c. And we're only going to use that later on. But we can first of all write this as p equals 1/2 x plus 3/4 y. So 4p is equal to 2x plus 3y. Rearranging now to have y on the left-hand side, I get 3y equals negative 2x plus 4p. And finally y equals negative 2/3 x plus 4p on 3. So let's think about what this means on my graph. So I'm going to draw a really bad graph here. So here's my graph, and I've got out here I'm going to have a bunch of constraints, and they are going to give me my feasible region. Right? So the feasible region will be this big area all in here. Okay, and this function here is my objective function. So what we can think about doing is starting off when profit is 0. And we're going to hold the profit constant and look at all of the combos that can make that up. So when p is 0, my line will just be y equals negative 2/3 x. So if I take my ruler, I can draw the line on like this. Right? And then I decide I'm going to change p, and we'll put p up to 1. So when p is equal to 1, the line's going to move up and out. It's going to be parallel. So we can take the ruler and we can just shove it out a tiny little bit here like this. Whoops. There's my new profit line. So what our goal is when we do linear programming is to keep on pushing that line out as far as we can, but still be in the feasible region. Okay, so you can see that ruler moving out there. When we check our corners, that's what we're doing. Now, I'll give away the punchline here. In part A, we're going to find that the profit is maximized at one of these corners, and I think it's going to be this one here. We'll see it when we get to it. When we change to part B, what we find happening is that instead of having one point be the best point, we get a whole little group of points, and it's all to do with the gradient of the objective function, right, which is here, and the gradient of the constraints. So that's what we want to be on the lookout for. Right, that was a very long diversion away from the achieved stuff. So let's do what I said I'd do and do the easy stuff first. So we go back to here, we've got our ordinary old profit function, and we've got our variables. The next thing we have to do is to write the constraints, and they're very easy if you've done lots of practice by now. So x plus y is less than or equal to 40, that's the oven constraint. X up to 30 mini pizzas, x has to be less than or equal to 30, y has to be less than or equal to 20. Both of those things have got to be 0 or greater. And then the last one we've got to do is the time constraint. So 3 minutes for each stuffed potato in 1 minute for each mini pizza means that the constraint is going to be x plus 3y must be less than or equal to 72 minutes. So we chuck those into Desmos and we figure out where our vertices are. So we've done variables, objective function, and constraints. Now we're going to try and find the graph that I put in. Okay, here's the graph here. And as usual, we reverse the constraints when we put them into Desmos, and then we're going to go and work out the profit at each of these vertices. Okay, so showing you again this idea of the slider without using a slider, we know that my line has got to have a slope of negative 2/3. So the line that I'm pushing out has got this slope here. And you can see that that ruler is going to be pushed out the furthest at that slope at that point 2416. Okay, so that's a very, very low-tech way to show you what's going on. And if you're in my class, you will have played with using a slider in Desmos. You don't have to do that at all in the internal for any of it, but I think that seeing it visually really helps. So let's look at our little table. No, that's not the right little table. There's a nicely typed up little table somewhere in here. Where's it gone? Here it is here. And this is how you'll write it up, right, when you're doing an internal assessment. So this is the first part of any task. We've got our vertices, and we put them into the profit function, and we find that the best profit is going to be made when we have 24 mini pizzas and 16 stuffed potatoes. So what have I done in here? Well, I've got my coordinates, I've put them in the objective function, and I've set it out nicely in a table. Right, let's go back to part B. Where's part B gone? Right, investigate what would happen to the total profit of the canteen if they reduced the profit from the mini pizzas from 50 cents to 25 cents. So our profit function would change, and it would be 0.25x plus 0.75y. So first I'm going to show you what do I need to do. Well, I don't change anything in my graph, right, because the constraints haven't changed. So all we've really got to do is to go back to our table, and we've got the coordinates, and we just have to check each of them with the new profit function. And this is what we discover. So when I put them in the new profit function, I get out these values here. And so pause the video and make sure that you're doing this as I go. So what we notice in here is that instead of having one point that is the best point, suddenly we've got two combinations that are giving me the same best profit, and it's $18. So first of all, why has it come down? Well, it's come down because we dropped the profit on the x's, what are x's? Mini pizzas, right? So the objective function changing means that the profit will have fallen for any of those things. But instead of there being one clear solution, we've now got that they don't care if they make this one or this one. But that's not the final answer. What's going on in here is that instead of having just two places where they're making $18 of profit, right? So we know they're making $18 of profit here, and they're making $18 of profit here. But that's happening because the gradient of my new profit function is the same as the gradient of this constraint here. So what that means is that anywhere on that line segment that is an integer combination is going to give me $18 of profit. And you can see where those integer combinations are by remembering how we did graphing back in year 9. Right? So my profit function has got a gradient now of negative 1/3. So we go down 1 and out 3, and we'll hit another integer value. Right, down 1, out 3, and so on. So what we need to do is to figure out these points, and then we're going to explain that all of them will give me the same combination. So some of you will have long since stopped watching. If you're still watching, hang in there, because I want to show you how to rearrange the new profit function and look at what's happening on the graph. Okay, so P is now equal to 1/4 x plus 3/4 y. 4P is equal to x plus 3y. 3y is equal to negative x plus 4P. y is equal to negative 1/3 x plus 4p over 3. But we can see what's going on up in here, and we know which constraint it is that it looks like we're getting the multiple solutions on. It's this purple line here. So which constraint is that? Well, if we go back to looking at how we set that up, that's the constraint about the time in the oven. Okay, so that oven constraint had this form. It had x plus 3y is less than or equal to 72. So rewriting this gives me 3y equals negative x plus 72. Y equals negative 1/3 x plus 24. So look, this is my constraint for the oven, sorry, not for the oven. This is the constraint for the time spent. And this is my profit function. And you can see that the gradient of these two is the same. And so that's why I'm getting multiple solutions. So what do I need to do? Well, I need to find those integer combinations. Okay, so you can do that. I've done that over here. No, I haven't. I've written up for you so you can pause the video and go through this, what's happened with the two cases, right? So this is before the profit change, and then this is after the profit change. So my combinations that I've got to check out are now these. I've got 12 and 20. And I know that at the end of that line segment, I've got 24 and 16. So now we're just going to fill in the gaps with all of the integer valued ones. So I'm going to go, my gradient's negative 1/3. So I'm going out 3 and down 1. So it's going to be 15 and 19, 18 and 18, and 21 and 17. And if we put the profit in here, we can see that we end up with $18 in each case. So this one will be 3 plus 15 gives me 18. This one will be 375 plus 1425 equals 18, and so on. So all of them will give me the same combination. And this last one here, 525 plus 1275 equals $18. So that's your first example of a situation where we get multiple solutions. What we want you to be able to do is to explain clearly what's going on. And it's kind of important that you can show us that it's not all of the points along that graph. I'm just trying to find the graph. That's why I'm skipping between slides so annoyingly. Sorry about this. Here's my graph. Here. It's not actually, in real life, the whole of that line. It's only the integer points on that line, right? So it's this one, this one, this one, and so on down to here. And that's what we want to see you work through. Okay, so that's parts A and B. In part C, there's a really good question about changing the oven capacity, and then part D's got another one about changing another thing around. You can see that these are much slower going than the earlier ones, so I'll do another video later on today on those two questions. Thanks for watching. Please leave me any comments or let me know if there's any mistakes in it.